All right, hello chemistry class. We are looking at chapter 9, and kind of like chapter 8, there are going to be a lot of previous concepts and knowledge that you need to make sure you understand when we dive into chapter 9. A lot of things are going to come together here, things that we've talked about previously, and that's the neat thing about chemistry is all this information now is going to be applied here in chapter 9 as we look at something called stoichiometry. That sounds like a very complicated thing, but it's not. It's simply working with balanced chemical equations to take a known quantity, an amount that you know in the reaction, and trying to find something that you don't know. Okay, try to find some unknown. Now, one of the best ways to work through chemistry or through stoichiometry in chemistry is actually to work through some examples. So in this first section of chapter 9, there's a lot of information here about what is stoichiometry. We talk about composition stoichiometry, which is basically just looking at elements in a compound, or we look at reaction stoichiometry, which means the relationships that are actually in a chemical reaction. And this is what we're going to be focusing on in this chapter, reactions. What are the relationships in reactions between reactants, products, etc.? Okay? Now, as mentioned here, there's a lot of information that talk you through some different concepts as related to stoichiometry. But I think the best way to understand stoichiometry and what we're going to be doing with stoichiometry is to actually show you some examples. And I have a way to set this up for you so that if you follow the steps, you will always get the right answer and you'll always understand how to use stoichiometry to find some unknown quantities. The major thing that you must understand in stoichiometry is the idea of the mole and mole ratios. Okay? So let's look at this reaction right here. I'm going to rewrite it over here for us, just so that I can add a few comments. Okay. If I read this, what the reaction is that is described here, we're saying basically we have two compounds of aluminum oxide. Two compounds of aluminum oxide are going to decompose, they're going to break apart and form 4 atoms of aluminum and 3 molecules of oxygen. Okay? So what we're saying here is you see these coefficients. This is balanced now. Remember in the previous chapter we had to balance our reaction? You have 4 aluminums on both sides, and you have 6 oxygens on both sides. Now, these coefficients are telling us in what ratio these 3 items will react in this particular reaction. So what we're saying is it's always going to be in a ratio of 2 parts of the aluminum oxide are always going to yield 4 parts of the aluminum and 3 parts of the oxygen. So that could actually mean, it really actually could mean 2 compounds of aluminum are going to produce 4 of the, 2 compounds of the aluminum oxide can form or will produce 4 atoms of aluminum and 3 molecules of the oxygen. It could be actual particles that we're talking about. Or we could double everything. We could say 20 of these, 20 of the aluminum oxide, and that means it would produce 40 of the aluminum and 30 of the oxygen. So as long as it is in a 2 to 4 to 3 ratio, these numbers can be multiplied, doubled, multiplied by 10, 100, or whatever, and you would be able to find the other ones as long as you know the ratio. So for example, if this, I know if I have 200 parts of the aluminum oxide, I know then the amount of aluminum that's going to be produced has to be 400 parts of the aluminum. And the oxygen, there have to be 300 parts. Always in a 2-4-3 ratio. Always. Okay? I could even go as high as using a mole. If you remember, 1 mole is a huge number. 6.022 times 10 to the 23rd. So I could double that number, okay? 2, I could say 2 times that number. And for aluminum oxide, how much aluminum would be produced? Well, 4 times that number then, because it's a ratio of 2 to 4. 4 times 6.022 times 10 to the 23rd. And 3 times that number would tell me how much oxygen is produced. Remember, it always has to be in the same ratio. It always has to be a 2 to 4 to 3 ratio. 20 to 40 to 30 is a 2 to 4 to 3 ratio. 200, I just multiplied everything by 100, right? 200 to 400 to 300 is a 2 to 4 to 3 ratio. 2 times Avogadro's number, 4 times Avogadro's number, 3 times Avogadro's number. That's still a 2 to 4 to 3 ratio. Remember this number right here, this Avogadro's number, 6.22 times 10 to the 23rd? As I said, that's a mole. So I could also say, well, these aren't just compounds and atoms, 2 compounds producing 4 atoms and 3 molecules. These actually could be moles. You could say this 2 moles of aluminum oxide is going to produce 4 moles of aluminum and 3 moles of oxygen. This is what we're going to see and hear and talk about way more than talking about individual molecules or atoms or compounds. Okay? So these coefficients right here are going to represent how many moles of each substance are reacting in this particular reaction. Okay? And if we know one of them, if we know how many moles or how many particles of one of them, we should be able to find all the others because we know the ratio in which they are going to react. Okay? Always. If you know the moles of one of them, the number of moles of one, and you know these coefficients, the mole ratios, you can find the number of moles of the others in that reaction. Okay? Let me give you an example here. Looks right here. It says, using this reaction that we just talked about, here's this question. It says, how many moles of O2, how many moles would 13 moles of the aluminum oxide produce? Well, I just have to look right here. The reaction is always a 2 to 4 to 3 ratio. So how many moles of oxygen? That corresponds to the 3. If I have 13 moles of aluminum, that's this one, 13. Okay? Well, if I look at aluminum oxide, which is the 2, as compared to the oxygen, which is a 3, it is a 2 to 3 ratio. A 2 to 3 ratio. So all I do is I take the 13 moles of aluminum oxide and I need to multiply by a ratio. These are in a 3 to 2 ratio. Oxygen and aluminum oxide are in a 3 to 2 ratio. So I know for every 3 moles of oxygen that are produced, I needed 2 moles of the aluminum oxide. I use this ratio and I set it up this way so that I know the moles of aluminum oxide are going to cancel. So I'm multiplying by 3 halves. And then I'll take 13 times 3 halves. So 13 times 3 halves is what? 39 halves, which, you come down here, is going to be what? 38, so that's going to be 19 and a half moles. Okay? 19 and a half moles. Alright? So you can always figure out how many moles of something in the reaction if you know the number of moles of something else and you have the mole ratios. You have these coefficients. Those coefficients are expressing the mole ratio in a particular reaction. Okay? Now, at some point, we're also going to be talking about mass. And remember, in order to go between mass and number of moles, we have to use the molar mass. The molar mass, if you remember, it's the mass in grams of 1 mole of that substance. And where do we get the molar mass? We get the molar mass of elements straight from the periodic table. Okay? So for example, all you do is you look on the periodic table, and right underneath the symbol is going to be your molar mass. So right under the symbol for aluminum, for example, you're going to see 26.98. Now if you say the units are grams, if you say 26.98, 26.98 grams is going to be the mass for 1 mole of aluminum. 6.022 times 10^3 atoms of aluminum are going to have a mass of 26.98 grams. All right? The molar mass of oxygen, just look on the periodic table. Well, the molar mass of oxygen is 16, but oxygen is always O2. So there are 2 per molecule. So O2 has a molar mass of 32 because each oxygen is 16. And if we combine aluminum and oxygen in a molecule, or in a compound called aluminum oxide here, we've got 2 aluminum and 3 oxygen. So we would take 2 times 26.98, 2 aluminum, plus 3 times 16. There are 3 oxygens, 3 times 16, and we would get 101.96. Let me write that down. I'm taking 2 times 26.98, that's for the 2 aluminums, plus 3 times oxygen is 16, 3 times 16, 15.99, something like that. And when you do this calculation, 2 times 26.98 plus 3 times 16, you should get something close to 102. Okay? That's the molar mass of aluminum oxide, Al2O3. Okay? So, what if you are told the number of moles of something and you want to find out the mass of that? Well, if you are told how many moles you have of something, you simply multiply by the molar mass to find out how much that weighs, what the mass is of that. So for example, if you've got, let me just keep it simple and then we'll go to this example. If you've got 1 mole of aluminum on the periodic table, you are told that that has a mass of 26.98 grams. So 2 moles of aluminum would just be 2 times that, right? Just be 2 times 26.98, all right? And 3 moles would be 3 times that. Well, 26 moles is just going to be 26 times the molar mass of aluminum. You get 701 grams. That's the mass of 26 moles of aluminum, because each mole of aluminum has a mass of 26.98. Okay? All right. Let's just look at a couple examples here, even though you don't have to do these as part of the assignment, but I just want to do a couple examples, and you can write these in your notes. These are great examples for you to write down in your notes. Okay? This says right here, write in all the mole ratios. So basically we're saying the mole ratios here, it is a 2 to 2 to 1 ratio. How did I get that? Just look at the coefficients. Okay? Look at the coefficients. This reaction always happens in a way so if there's 2 parts mercury oxide will produce 2 parts mercury and 1 part oxygen gas. Okay? So if you need to convert from one to the other, you might have to set up a ratio of, you might have to use this 2 to 2 ratio. You might say 2 moles of mercury oxide to every 2 moles of mercury. That's one possible ratio you might have to use. This ratio right here, 2 to 2. Or if you want to go between mercury oxide and oxygen, that's a 2 to 1 ratio. That's another ratio you might have to use. You might be using a 2 to 1 ratio, where this is the mercury oxide and this is the oxygen. Okay? Or you might have to flip them. If you go in the other direction, you might have to flip them. Okay? You might have to flip the ratio and use it the other direction. You might have to use a ratio of 1 oxygen for every 2 mercury oxide, depending on where you're going, how you're doing this. Actually, that would be used going this direction. But you can see we can set up multiple ratios by looking at the coefficients in the reaction. Okay? I'll show you how this plays out with some very specific examples. We're going to be looking at the calculations that we do in stoichiometry, stoichiometric calculations, and these are going to be assumed to be under ideal conditions, meaning that the reaction is going to happen perfectly. All the reactants are going to be used up to create as much products as we possibly can. There's no air, there's no waste, there are no mistakes. It's ideal conditions, okay? Which doesn't really happen in the lab, it doesn't happen in experiments, it doesn't really happen in real life, but we're going to assume that we have ideal, perfect conditions, okay? Now I'm going to actually show you some problems. I'm going to walk you through this and show you exactly how we can do this very simply and easily to do the stoichiometric calculations. Okay, here is a reaction. We have 1 part, or you can say 1 mole of carbon dioxide reacts with 2 moles of lithium hydroxide to produce 1 mole of lithium carbonate and 1 mole of water. It has to be balanced. This has to be balanced in order to use these calculations. Must be balanced. Okay? Now the question is, how many moles of lithium hydroxide, that's this right here, are required to react with 20 moles of carbon dioxide? Now, we look at our reaction, obviously it says we have 20 moles of carbon dioxide, but that's not the number in front of carbon dioxide. The number in front of carbon dioxide is 1. So we, in our reaction, are showing we have 1 mole, but now we are doing an experiment and we have 20 times that. We have 20 moles. But the ratio has to be the same. So this reaction is always occurring in a 1 part carbon dioxide to 2 parts lithium hydroxide to 1 part lithium carbonate to 1 part water. That's the ratio of those 4 species in this reaction. And now we're told, well, what if you have 20? Well, all you do is you just multiply everything by 20, because the carbon dioxide was 1 and now it's 20. So it got multiplied by 20. So we're going to multiply everything by 20. So this is going to be a 20 to 40 to 20 to 20 ratio. And what is the question? How many moles of lithium hydroxide? That's this one. Well, it's got to be 40. Okay? It's got to be 40. Now, using a ratio, I'll show you the calculation that you might like to use. It simply looks like this. We are told that we have 20 moles of carbon dioxide. Okay? 20 moles of carbon dioxide. And by looking at and comparing lithium hydroxide and carbon dioxide, they are in a 1 to 2 ratio, or you might say a 2 to 1 ratio. So I use that ratio to convert. I'm putting 2 moles of lithium hydroxide over 1 mole of carbon dioxide. That's the ratio in the reaction. These numbers right here, 2 and 1, are the coefficients in front of lithium hydroxide and carbon dioxide. How do I know I want the lithium hydroxide in the numerator and the carbon dioxide in the denominator? Because I want to cancel moles of carbon dioxide, so that has to be in the denominator. And so that tells me the operation I need to do. I need to take 20 moles of the carbon dioxide and multiply by a ratio of 2 to 1. And when the moles of carbon dioxide units cancel, I'm left with moles of lithium hydroxide. 20 times 2 is going to tell me I need 40 moles of lithium hydroxide. Okay? Let's work with another one here. Let's see. Okay, we can do this one. Alright, this one here. Now, this is a little more involved because we are given the information in words. So we're going to have to do what we did last chapter and convert the words into a chemical equation, balance it, and then answer the question that we are being asked here. Okay? So it says the decomposition of potassium chlorate. Okay, potassium chlorate, KClO3, is used as a source of oxygen in the laboratory. How many moles of potassium chlorate are needed to produce 15 moles of oxygen gas? Now we have to know what the reaction is here, and so I'll just give it to you. So it's going to decompose, potassium chlorate is going to decompose into potassium chloride and oxygen. We're told that it's going to produce oxygen. The other product is the potassium chloride right here. Okay. Now we have to balance this. We have one potassium on both sides. We've got one chloride on both sides, but we've got 3 oxygens on one side and 2 on the other side. So we are going to have to double this compound and triple the oxygen. Now we've got 6 oxygens on both sides. But that also doubled the potassium and chloride, so I have to double this guy right there. Okay? Double the potassium chloride. Now we have a balanced chemical reaction that we can use, and the mole ratios are 2 to 2 to 3. Okay? 2 to 2 to 3. That is given. And they always are going to react in that ratio. So now we're asking this question. How many moles of potassium chlorate, that's this guy right here, potassium chlorate, are needed to produce 15 moles of oxygen? Well, to produce 3 moles of oxygen, I needed 2 moles of the potassium chlorate. Now I'm asking, well, what about 15? And you should be able to see that's 5 times as much. So I'm going to need 5 times as much of the potassium chlorate. So it's got to be a 10, because it has to stay in the same ratio of 2 to 3. 10 to 15 is a 2 to 3 ratio. Now again, mathematically, here's the calculation you can do. You would take this 15 moles of oxygen, which is given to you, 15 moles of oxygen, and you want to go back the moles of potassium chlorate. So what is the ratio that you must stay in? You have to stay in a 3 to 2 ratio, or a 2 to 3 ratio, because I'm going to multiply by 2 moles of potassium chlorate over 3 moles of oxygen. Why did I put the 3 moles of oxygen in the denominator? Because I started with moles of oxygen, and so I want to cancel moles of oxygen. So now I do this calculation, 15 times 2/3. Well, 15 times 2/3 is going to give me my 10. 10 moles of the potassium chlorate. Okay? So now what we want to do, we did just a second ago, we went from moles of something to moles of something else. That's one thing that you might be asked to do. But we're also going to take it one step further, and we're going to look at what if you need to go from moles to grams, or grams back to moles. From moles to grams, or grams to moles, or grams of one thing to grams of something else. Mass of one object to mass of a different object. Okay? Now, this is a lot of calculations right here, and they're showing you all the calculations, but I'm going to show you kind of a way that if this helps, you can set it up this way and do it the same way every single time. Okay? And I set it up usually kind of with a chart. So I'm going to show you that right now and give you a little example here for that. Okay? I'm going to use this example. I'm going to use this example right here. It's a fairly simple reaction. We have magnesium burning in air, and when that does, it combines with oxygen to produce magnesium oxide. Okay? Now I'm going to write out that reaction. 2Mg plus O2 yields 2MgO. And now I'm going to make a little bit of a table here. Alright? Under each of these, I'm going to have some quantities that I should be able to find. So, the first thing I'm going to write down here is I'm just going to write down the number of moles. Okay, the number of moles. And then I'm going to also need the molar mass, that's mm, and down here I'm going to put mass. So moles, molar mass, and mass. The reason I'm doing those three is because to go from mass to moles, you have to use the molar mass. And to go from moles back to mass, you use the molar mass again, but just in the inverse method. I'll show you what I mean in a second here. Watch. So I have a bit of a table here. Okay. The coefficients, remember, are my molar ratios. I know that these have to react in a 2 to 1 to 2 ratio. Always 2 to 1 to 2 ratio. Not masses. Listen carefully, listen carefully. That ratio is not for mass. That ratio is for moles, quantity, not mass. Okay? So if you are given mass, you have to go to moles to use the coefficients. Watch. The question here is, what mass in grams of magnesium oxide is produced from 2 moles of magnesium? So I am given 2 moles of magnesium. I'm going to put that right here, 2 moles of magnesium. Now this number that they gave me, it didn't have to be the same as this coefficient. It could have been 4 moles or 3.5 or half a mole. But it just happened to be we are using the number of moles that is the same in the reaction, the coefficient of the reaction. So we're told we have 2 moles of magnesium. Okay, but I want to find out something about what? The mass, I'm sorry, yeah, that's right. I want to find the mass of magnesium oxide, which is over here. I want to find this quantity right here. That's what I want to discover. So what I must do, I can't go directly from moles of magnesium to the mass of the magnesium oxide. I have to use these coefficients right here to go from moles of magnesium to moles of magnesium oxide. I want to cross over from there to there. Anytime you cross from one column to another column, you have to use the coefficients, the molar ratio. So I look at the molar ratio, and I know that magnesium and magnesium oxide always react in a 2 to 2 ratio. In other words, it's the same quantity. Whatever magnesium is, that's how much magnesium oxide is going to be produced. So I know this is also going to be a 2. Then I can't stop there, because I'm not just asked for the number of moles of magnesium oxide, I'm asked for the mass of that. Well, then I have to find the molar mass of magnesium oxide. So I look on the periodic table, and on the periodic table, magnesium has a molar mass of 24.3. 24.3 grams. Okay, magnesium oxide. Oxygen has a molar mass of about 16. We're just going to round it off to 16 there. Okay, it's 15.99. Okay, but 16 is fine. So we have what, 40.3 grams is going to be the molar mass of magnesium oxide, the two together. So what I have to do is I use that to go from moles to the mass of those 2 moles. Each mole is 40.3 grams. I have 2 moles of the magnesium oxide. So 40.3, I need to multiply by that, multiply by 40.3, and I'm going to get 80.6 grams for the mass of magnesium oxide when it reacts with 2 moles of magnesium. Okay? Let me do another example. Actually, let me set this up and I'll show you. Okay? So let's say we have something like this. Here's a general reaction, and I suggest you set up a table. Now, some of you will be able to see the mathematical calculations fine. You won't use a table, no problem. Okay? But I suggest you talk about moles molar mass, and mass. Okay? And if you want to go between these quantities, you're going to use molar mass to do that. And you're going to use the molar ratios. Okay? So here's the deal. Anytime, as I mentioned before, you go from one column to the next column, if you want to go from moles of something to moles of something else, you can't go directly mass to mass. We don't have that ratio. We only have ratios for the moles. The X, Y, and Z are the coefficients. Those are your mole ratios. So to go from moles of something to something else, you have to multiply by the mole ratio. Okay? You have to multiply by the correct mole ratio. To go from moles down to mass, if you know the number of moles and you know the molar mass, then you would multiply by the molar mass. Okay? You multiply by the molar mass. If you are going the other direction and you know mass and you want to go up here to moles, then you divide by this molar mass. Molar mass gets you between moles and mass in one column. This is in one column. So if I want to go from moles of species C down here to the mass, I would multiply by the molar mass of whatever C is. If I want to go the other direction, I would divide by the molar mass of whatever C is. If I want to go from this column, okay, if I want to go from C to B, you only can do that using mole ratios. Okay, so I'd have to multiply by the correct mole ratio. Then I could go from, okay, if I want to go from C to B, I have to find out the number of moles of C. Then I can go over here to B, find the moles of B. Then if I need to find the grams of B, then I would have to multiply by the molar mass. Okay, so let me show you a couple examples here on how we can do this. Okay, so I'm going to use my table. I have a reaction here of carbon dioxide and water producing basically, I believe that's sugar and oxygen. Okay, so this is a process of that would be happening maybe like in a plant that's going to take the carbon dioxide along with water and convert it into glucose and oxygen. Okay, so we have here, let me rewrite this whole thing for us. All right, and I need moles, molar mass, and mass. Now, in this problem, we are told the following reaction produced 10 grams of oxygen. So I can put right here in the row for mass under oxygen, I'm going to put 10 grams. We are told that mass of oxygen is produced. Okay? Now, I know the question here is a little bit different, but what I'm going to do is I'm going to show you how I can find any other quantity in this reaction if I just know one. And I know the mole ratios. So 1 there, 6 and 6. So we're in a ratio of 6 to 6 to 1 to 6. So here's the deal. I could find any other value. Let's go way over here to, let's find out the mass of carbon dioxide that must be needed to produce these 10 grams of oxygen. I want to go from this 10 grams all the way over here to find out how much carbon dioxide must be used to produce those 10 grams. So all you do is, remember, to go from one column to the next, you have to use the mole ratio. So I've got to get to moles first. So I have to go from here to there. I have to go to moles. How do I do that? I use the molar mass. So I need to know the molar mass of O2. Well, the molar mass of O2 is 32 grams per mole. So if I've got 10 grams, that obviously is not 32. 32 grams is 1 mole. I only have 10. I have about a third of a mole. What is it exactly? I'm going to divide. I divide here, going this direction, I'm going to divide by 32. So this is going to be 10 divided by 32. That's going to give you about 1/3. Okay? Okay? The calculation is about 0.31. That's about 1/3. Okay? So I don't have a full mole. Remember, a full mole would have been 32 grams. I only have 10 grams. I only have a fraction of a mole right there, 0.31. Now I have to get all the way over here to carbon dioxide. Well, the way I go from one column to another column is not through the mass. I cannot go 10 grams directly to my answer over here for mass of carbon dioxide. I have to go over and use, over this bridge here, uses the mole ratios, the coefficients. So now what do? Well, I know that if I have 0.31 moles here, then I have to have the same number of carbon dioxide. Why? Because it is a 6:6 ratio. They're exactly the same. The calculation actually is this: 0.31 moles of oxygen times 6 moles of carbon dioxide for every 6 moles of oxygen. Moles of oxygen will cancel, and I multiply by 6/6. I know that's just 1, but I wanted to show you the mathematical computation. So once I do that, this is going to be 0.31 as well. Now I can go from the number of moles of carbon dioxide down here to the mass of that carbon dioxide. How do I do that? Using molar mass. This time I'm going to multiply. So I have to find the molar mass of carbon dioxide. Well, carbon's molar mass is 12. 2 oxygens, it's going to give me a molar mass of 16 times 2, 32. And so it's going to be about 34 grams per mole. And so I multiplied by that. Okay? So I'm going to take my 0.31 multiplied by 34, and we get 10.6. Okay? So this answer right here is 10.6 approximately grams of carbon dioxide. Okay? Now, this method, you can go anywhere. You can find any value. All you have to be given is 1, whether it's mass or moles, and you can find any other value in this table as long as you know one value and you know the molar ratios. Okay? Let's do one more example here, showing you that I can find anything else. Let's imagine, I'm just going to make something up. Let's imagine that I am given let's say we're given something here with water. Let's say we're given the mass of water in this reaction. And let's say we're given 10, we'll use 10 again, 10 grams of water. Okay? We're going to have to ignore these values now. These values are from the previous example. Just ignore those. 10 grams of water, and we want to figure out what would the mass be of sugar that is produced, of the glucose here. So 10 grams of water, I need to go from mass to moles of water, then over the molar bridge to the moles of sugar, and then from there down to the mass of the sugar. Remember, when you go up from mass to moles, I'm going to divide by the molar mass. If I go down, I'm going to multiply by that particular molar mass. Okay? So if I have 10 grams of water, the molar mass of water is 18. Each oxygen is 1, so that's 2. I have 2 oxygens. Hydrogen. Each hydrogen is 1, so there's 2 of them. Each oxygen is 16, so that's a total of 18 grams per mole. So I have to take 10 divided by 18. Okay? So 10 divided by 18, and I get 0.55, 0.56 about. Okay? That's the number of moles. I have about half a mole. Look, I only have 10 grams. I don't have 18 grams. 18 is a full mole. I only have 10. That's about half a mole. Now I go from here over to the moles of the glucose. Well, they are in a 6:1 ratio. Only a sixth of the amount is formed of glucose compared to the amount of water that I have. So what is the calculation I have to do here? I have 0.56 moles of water, and for every 6 moles of water, I produce only 1 mole of the glucose. 6 moles to 1. Moles of water are going to cancel, so I'm going to take 0.56 times 1/6. 0.56 times 1/6, okay? All right, so we get what, 0.09, 0.09 right here, 0.09 moles. 0.09 moles of this glucose. It's a sixth of what was about a half, right? So I have a very small amount of moles here. Then I have to multiply to go from moles of glucose to the mass of that. I have to multiply by its molar mass. Okay? I'll just look up the molar mass for glucose really quickly here. So the molar mass of glucose is about 180. Again, how would they have gotten that? Well, 6 carbons, so that's 6 times 12, plus 12 hydrogens, that's 12 times 1, plus 6 oxygens, that's 6 times 16. We add that all up. So we take 0.09 times 180, and whatever that value is, that tells you the mass of glucose that was produced from 10 grams of water in this reaction. Okay? And we could fill in any box we wanted to just by using molar mass to go between mass and moles. Remember, to go from mass to moles, you divide, or to go from moles to mass, you multiply by the molar mass. And then to go from moles of one to moles of the other, you use the mole ratios, these coefficients. Okay? Remember, you only can go from one column to another column by using the moles and the mole ratio. So if you want to, notice if I was given mass here of the water and I want to get the mass over here, I had to go up to moles, use the mole coefficients, use the coefficients, the mole ratios, and then from there go down to the mass of the glucose. Okay? All right, let's do one more here, because this is something that you have to master. This is something you've got to get. Okay, we are told here that we've got the production of nitric acid. First step is the catalytic oxidation of ammonia. Okay, all right. So we're going to take ammonia here, and we're going to turn it into NO and water. This is unbalanced. You must balance it first. So let's go ahead and balance this, see if we can get this balanced. We have 1 nitrogen on both sides. That's taken care of. We have 3 hydrogens on this side, and only 2 on this side. So I'm going to have to multiply this water by 3 and this hydrogen by 2. Now, of course, that's going to alter the number of oxygens and nitrogens, so I double check now. I have to go back because I just doubled the ammonia here that has nitrogen in it. Now the number of nitrogens has doubled, so I have to multiply this by 2 as well. Now let's see how many oxygens I have. I've got 2 in the reactant side, and I've got 2 and another 3. That's 5. 5 and 2, or sorry, 3 and 2, that's 5. So I'm going to multiply this by 5 halves. Why did I do that? Because 5 halves times 2 is going to give me 5. Now, we usually don't leave fractions in our balanced equation with as coefficients. So what I'm going to do is I'm going to multiply everything by 2. So I get rid of this fraction right here. I'm going to multiply by that denominator. So I multiply everything by 2. And so here is my balanced equation. Remember, I multiply everything by 2. So it's 4 NH3 plus 5 O2. It's going to produce 4 NO and 6 H2O. So I'm going to have moles, molar mass, and mass. Okay? In this problem, we are told the reaction is run using 824 grams of ammonia. So I'm given this number right here, 824 824 grams, mass of ammonia. Okay? And it says excess oxygen. That just means we got plenty of oxygen. The atmosphere is full of oxygen. You'll never run out of it. Don't worry about it. Okay? And we are asked how many moles of NO are formed. I'm actually going to take it one step further, and we're going to say what mass of NO is formed. So I want to find this right here. That's the one that I'm curious about. Okay? So all I do is I can't go directly from mass to mass. So I'm going to go from mass of ammonia up to moles of ammonia. How do I do that? I have to divide by the molar mass of ammonia. So I have to find the mass of ammonia. I look at my periodic table, okay? On the periodic table, nitrogen is 14. Each hydrogen is 1. So that's 14. Nitrogen is 14. Hydrogen is each 1. So that's 14 plus 3 is 17. Okay, just 1 mole, not 4. Even though there's a 4 there, I don't care about the 4 right now. I'm just finding the molar mass, just 1 mole. So 14 plus 3 is 17. 17 grams per mole for ammonia. I have a lot more than 17 grams. I've got 824. So obviously I have more than a mole. I take 824 and divide by 17. So 824 divide by 17, and that's going to give me the number of moles. Okay? 824 divided by 17, 48.5, let's say. All right? So this is 48.5 moles of the ammonia, 48.5. Now I can go from ammonia over here to the NO, nitrogen oxide, all right, or nitrogen monoxide. So what do? I look at the ratio. Well, fortunately, it's a 4-to-4 ratio. That makes it really easy. Whatever this mole is, this mole is. So it's 48.5 moles as well. We're taking this one step further. What is that mass? The 48.5 moles of the NO is what mass? Now I need the molar mass of NO. Well, NO, N is 14, oxygen is 16, so we're at 30 grams per mole. And when I go this direction, I want to multiply. Okay? So if I have 48.5 moles, and each mole is 30 grams, well, that's 48.5 times 30. Okay? 48.5 times 30. That's going to give me about 1,454, approximately 0.1. Okay, we'll just round it off here. So 1,454.1 grams. And that's how much of the NO is produced from 824 grams of the ammonia. Okay? Now, all of these calculations are showing you exactly what I'm doing. Okay, these boxes and these calculations are doing exactly the same thing. Same exact calculations. They're just writing it out in, kind of a diagram so you can see what's going on here. Okay? Let's do one more here. It says how many grams of SNF2 are produced from the reaction of 30 grams HF with SN. And they're giving us the reaction there. They're giving it to us, and I think it looks like it is balanced. It is balanced. So all I'm going to do is I'm going to rewrite this just so I have some space. Okay. These coefficients are telling us the ratio. 1 mole of tin plus reacts with 2 moles of hydrogen fluoride, hydrogen monofluoride, yep, are going to produce 1 mole of tin fluoride and 1 mole of hydrogen gas. That's the ratio in which they react. It doesn't mean we have to have 1 mole. We could have 2 moles, 3 moles, a half a mole, whatever. But they have to react in this ratio. Okay? Molar ratio. Those are the mole ratios. So we are told that we have 30 grams of HF. So again, moles, molar mass, and mass. We are told 30 grams of HF. So that's this one right here, 30. We are given that number. What do we want to find? We want to find out how many grams of SNF2. We want to find this one right there. So I'm going to walk you through the process. You are going to go from 30 grams of HF up to its number of moles. Then you have to find the mole ratio to cross over that bridge from one to the other. And then from there, you got to go down here. So how do we do that? I'm not going to do all of the calculations, but I'm just going to show you the steps. So we'd have to find the molar mass of HF. Okay, the molar mass of HF, it looks like it's right there, 20, about 20. So I take 30 grams, which I'm given, and divide by 20. So I divide by 20, okay? So I'm taking my 30 grams, and I'm dividing by 20. That would give me this value right here. Then I want to go from moles of HF to moles of SNF2. Well, it is a 1 to 2 ratio. The moles of SNF2 is always half the moles of HF. So I'm going to multiply by this ratio, the mole ratio of 1/2. That's what they're doing right here. Okay? Now I'm going to go down to mass of SNF2. I'm going to have to use the molar mass of SNF2. It looks like it's 156.7 right there. And this is where you multiply. So that's what they're doing in this step. We're multiplying. So all of this calculation right here are the 3 steps that I just diagrammed. Divide by the molar mass of HF to find the number of moles of HF. Then multiply by the mole ratio of SNF2 to HF. Then multiply by SNF2's molar mass right there. And once you've done all that, you will have the correct mass of the SNF2. Okay? That's how you do it. Okay. I'll put some more examples. I'll go through the review questions for you, so there's lots more examples for that, okay? All right, and then we'll get into section 9.3, limiting reactants and percent yield. All right, in this section, what we're going to be looking at is something that's a little more realistic. Usually in a reaction, one or more of the reactants is in excess. What that means is we got lots of one of them maybe and not so much of the other. In other words, they're not in the perfect ratio that is expressed in the balanced equation. So what ends up happening is one is going to run out before the other, and the whole reaction is going to stop, because once one of them is gone, the other one has nothing to react with. So once one of the reactants is used up, the reaction stops. So in your notes, you should be writing down section 9.3, limiting reactants and percentage yield. That's what we're going to be looking at. And you should write this down, that basically a limiting reactant is the reactant, which one, that's going to stop or limit the amount of the other reactant that can combine and the amount of product that can be formed. Once one of the reactants runs out, once it's used up, the whole thing stops. It's done. And that's going to determine how much is produced and how much of the other reactant is used up. Okay? The one that did not stop or did not stop the reaction or did not get all used up, that's the one we call that the excess reactant. If we got plenty of it, excess. Okay? And the one that does stop it is called the limiting reactant. It's sometimes reagent or reactant, either word is fine. Okay? So let's look at this right here. Let's say we have a reaction between carbon and oxygen. Carbon and oxygen. And it's going to form carbon dioxide. Now, according to this is balanced. What we're saying is for every 1 part carbon, you need 1 part oxygen molecule to produce 1 part carbon dioxide. Okay? So if you've got five parts carbon and you've got 10 parts oxygen, well, they react in a 1-to-1 ratio. So for every one carbon, you need one oxygen molecule. Done. One carbon, one oxygen molecule. One carbon, one oxygen molecule. One carbon, one oxygen, one carbon, one oxygen molecule. Now from that reaction, you will form 1, 2, 3, 4, 5, the same number of carbon dioxide molecules. And what do you have left over? Well, 1, 2, 3, 4, 5 oxygen molecules are left over with nothing to react with. So what is your limiting reactant? Well, once these 5 carbon atoms were used, that's it. The reaction was stopped. These oxygen molecules have nobody else to react with, no other carbon to react with. Okay? So whichever one is used up first, that is called your limiting reactant. All right? Let me put it this way. Carbon and oxygen. They are in a 1-to-1 ratio. If you are told that you've got 5 carbons, okay, what do you need? You need 5 oxygens. Do you have 5 oxygens? Yes, you were given 10. Okay, you were given 10. What do you have? You have 10. You've got 5 more than needed. 5 more in excess. Okay? So you have to compare, take what you're given here for carbon and determine what you need from oxygen, and then look and see what you have for oxygen and compare. Do I have more than I need or less than I need? In this case, we had more than we need. Okay? More than we need. Now, what if I was given, what if it's the other way? What if I was given, we'll write this down here, carbon, oxygen. Okay, we don't need to look at the products right this second. Let's say that I was given 5 moles of carbon, only 3 moles of oxygen. Okay, in this case, well, if I have 5 carbon, I need 5 of oxygen, but I only have 3 of oxygen. In this case, I'm short 2. So what's going to be limiting? In this case, the oxygen is going to limit. Let's go the other direction. Let's look at it this way. If I have 3 oxygen, okay, I need 3 of carbon. What do I have? I have 5 of the carbon, so I have 2 in excess. This time the carbon is too much. I have 2 moles of carbon that are not going to be used up. Okay? So that's the idea with limiting reactants and limiting and excess reactants. Okay? There's a couple ways we can determine this. One way is to determine how much is produced, and whichever situation or whichever number of moles produce the less amount, that's going to be the limiting reactant. What I mean is, let's say we had 3 moles of oxygen, and then we could determine how much of the product is produced from that, assuming that carbon is in excess, and we'll see how much is made. Or we look at the 5 moles of carbon and we'll say how much is produced from that, assuming we have plenty of oxygen. Whichever one is the lesser amount must have been the limiting reactant. Okay, I'll show you some examples. Okay, here's a reaction. Notice the balanced equation. Here are mole ratios, 1 to 4 to 1 to 2. Okay? And it says if 6 moles of hydrogen fluoride is added to 4.5 moles of the silicon oxide, which is the limiting reactant? This time we're given amounts of both reactants, not just one of them. We're given amounts of both. Okay? Well, let's look at this. If I consider my ratios here, 1 to 4, you'll notice HF and SiO2 react in a 1 to 4 ratio. I need 4 times as much HF as I do the silicon oxide here, SiO2. 4 times as much. That's all you really have to look at. Well, do I have 4 times as much? Here's my silicon oxide, 4.5. SiO2 HF. They are in a 1 to 4 ratio. But I don't just have 1 and 4. I don't have an ideal situation here. I don't have ideal amounts. I have 6 and 4.5. Okay? 6 and 4.5. Well, if you look here, silicon, the amount of HF compared to the silicon oxide is 4 times as much. Do I have 4 times as much HF as silicon oxide in the actual mole amounts? No. Because if I did, I mean 4.5 times 4, 1 to 4 here, would be what, 16, 18. That's 18. I don't have 18. I only have 6. So I'll never use 18 up of the HF. I only have 6. So 6 is all I have, and once that 6 is gone, it stops. Okay? If you want to go the other direction, again, use the 6 and the 4.5. Go the other direction. Go this way. The HF is 4, the SiO2 is 1. It's a fourth. The SiO2 is a fourth of the HF. So what if I go this direction? If I take 6 times 1/4, well, 6 times 1/4 is 6/4, which is what, 1.5? Okay? Do I have at least 1.5 moles of the SiO2? Yeah, I got 4.5. I got plenty. So I got more SiO2 than I need to react with HF. This 6 moles of HF is in excess. That is in excess. Okay? Sorry, that is the limiting react. The 6 moles of HF is the limiting reagent. This is the limiting reagent, and the SiO2 is going to be in excess. How much in excess, by the way? Well, right here, let's use this information. If I have 6 moles of HF, once that's used up, I will have used 1.5 moles of the SiO2, but I have 4.5. So I have 3 moles of SiO2 in excess. These 3 moles will not be used up because this 6 moles of HF only need 1.5 to put them in a 4 to 1 ratio. And I'm going to have 3 moles of the SiO2 left over. Okay? That's what all of this calculation is showing you here. It's showing it to you, though, in a little bit of a different way. What they're saying is take your 2 mole amounts, the 4.5 and the 6, and see how much they would individually produce of the SiF4. So they're saying use those molar ratios. So if you have 6 moles of the HF and you multiply by the ratio here, it's a 4 to 1 ratio, 4 to 1. You produce 1/4 the amount of SiF4, and so you would get 1.5 moles of the silicon fluoride. Do the same thing with the 4.5 moles of the silicon oxide. How much silicon fluoride would that produce? And that is a 1 to 1 ratio, 1 to 1. So it's going to be the same, but you'll never reach the 4.5 moles of the silicon fluoride because once the 6 moles is used up, you've only created 1.5 moles of that. So this is telling me that hydrogen fluoride is my limiting reactant. So that's another way to do it. See which one is going to produce the lesser amount of any of the products in the reaction. Whichever one produces the less amount, that's your limiting reactant. Because as soon as this 6 moles is used up of the HF, you only made 1.5 moles of the SiF4. You'll never get to the 4.5 because this is going to be gone by it. Okay? Okay, let's look at another one here. This looks like it is balanced at first glance. Yep, we are balanced here. We're in a 1 to 2 to 1 to 4 ratio. Okay, let's do a couple things with this. First, it says, what is the limiting reactant? Well, let's determine that. When 0.75 moles of the dinitrogen tetrahydride is mixed with a 1/2 mole of the dihydrogen dioxide. That's actually hydrogen peroxide. Okay. So let's see here. If we have 0.75 moles of this one, we're comparing our two reactants here. You'll notice the ratio. It's a 1 to 2 ratio. So in order for that ratio to happen in the perfect ideal ratio, you need twice as much hydrogen peroxide as you do the dinitrogen tetrahydride. Okay? Well, do we have that? Let's see. If I've got 0.75 moles of the N2H4, I would need twice that of the H2O2 for it to combine in a perfect ratio. Do I have twice that? No, I only have 0.5. 0.75 doubled is going to be 1.5, but I only got 0.5. So right away I know H2O2 is going to be the limiting reactant. Okay? Let me just say that again. 0.75 times 2 equals 1.5. Do I have 1.5? No, I don't have 1.5 of the H2O2. If you want to go the other direction, 0.5 moles of the H2O2, how much of the N2H4 would I need to ideally and perfectly react with that? I need half the amount. So what's half of 0.5? It's going to be 0.25. Do I have 0.25? Yeah, I got 0.75. No problem. So this is your limiting reactant. Okay? 0.5 moles of the H2O2 is your limiting. Okay? All of that's going to be used up. And when it all is used up, you will have used up 0.25 of the N2H4. But you got 0.75. So you will see that 0.75 minus 0.25, you're going to have a half a mole of the N2H2 remaining in excess. Left over, didn't react. Okay? Okay, let's look at another one here. Iron oxide, and it looks like we're creating that from iron and water. Okay? And there are a couple questions here. Oh, good. We're talking about limiting reactant, talking about mass and mass. These are some great questions here that's going to kind of bring everything together. So if we look at this, first of all, let's determine what the limiting reactant is, because that's going to determine then how much is produced. 36 grams of the water and 67 grams of the iron. Notice the iron and the water are in a 3 to 4 ratio, or 4 to 3, whichever way you want to say it. So let's take this water right here, 36 grams of the water. 36 grams of water. And in order for them to react in a perfect ratio, I need them to be in a ratio of 3 to 4. So let's just see here, 3 moles of the, oh, this is grams. I need to find out how many moles that is. Ah, I can't use these ratios with masses. I have to find out the number of moles of that. Okay? So I need to find out 36 grams of water is how many moles. Oh, my apologies. Let's step this back a little bit here. 36 grams of water as compared to 67 grams of iron. You can't compare masses when you're looking at the limiting reactant. You have to compare moles. So 36 grams of water, let's figure out how many moles that is. 36 grams. And I know that 1 mole of water is 18 grams. Just look at the periodic table. Oxygen is 16, each hydrogen is 1. So that's going to be 18. So that's going to be 2 moles, and that's for the water. Okay? Iron. If I look at iron, iron's molar mass is 55.8. I've got 67. Yeah, 55.8. Okay? So 67, 1 mole of iron is 55.8. Okay, so oops, sorry. That's going to give me 1.2. Okay, 1.2. All right, so 1.2. Now let's see which one we have enough of and which one we don't have enough of. So let's take this one right here, water. Okay, I have 2 moles of water. My 36 grams of water is 2 moles. Well, I notice that water and iron react in a 4:3 or 3:4 ratio. So let's take this 2 moles of water, 2 moles of water, and to find out how many moles of iron I would need to perfectly react with that, I need to multiply by 3/4. 3 moles of the iron for every 4 moles of the water. So 3:4 ratio, that's going to give me what? 3/2 or 1.5. 1.5. 1.5. 1.5. Do I have 1.5? No, I don't. I don't have 1.5 moles of the Fe. So Fe is my limiting reactant. Okay? I only have 1.2. As soon as that 1.2 is gone, as soon as that's gone, then the reaction stops. Okay? 1.2. So if I have 1.2 moles of Fe, I'm going to need 4/3 of that, 4 to 3, 4 to 3, 4/3 of that to give me the number of moles of water that I need. So 1.2 times 4/3, okay, that's going to be 1.6, 1.6, 1.6. Do I have 1.6? Yep, I have 1.6, at least 1.6 of the iron. I've got, or sorry, of the, yeah, 1.6 of the water. I'm sorry, 1.6 of the water. Yep, I've got 2, so I'm okay. All right. So the iron is going to be my limiting reactant. I'm going to end up using 1.2 moles of iron. That's the 67 grams. 67 grams is 1.2 moles of iron right here. Once I use up those 1.2 moles of iron, I will have used up 1.6 grams of water. Of the 2 moles of water, I will only use 1.6. Okay, 1.6 moles of water. So I'm going to have 0.4 moles of water in excess. I won't be using that up. All right? Now, let's get to the question here. What mass of iron oxide is produced? Well, I don't want to use 2 moles of water because I will never use all 2 moles. I'll only use 1.6 moles of water. So I suggest you use the limiting reactant, the 1.2 moles of Fe, okay? And I have to go from that to moles of iron oxide. So right here, they are in a 3:1 ratio, a third. 1 mole of iron oxide for every 3 moles of the iron, okay? And then from there, from there, the mass, then I would multiply by the molar mass of that iron, okay? So whatever the iron oxide mass is, I bet maybe they have it here. Nope. Yeah, here it is. 231.5, okay? 231, I multiply by 231.5 for every mole of the iron oxide. Okay? So if you take 1.2 moles, multiply by 1/3, and then multiply by the molar mass of that iron oxide, that will give you the mass in grams of that iron oxide. Okay? And all the calculations that are done here are exactly what I just did in kind of one step. All right? Okay, last part of this, and like I said, there'll be more problems like this in the review questions for you. All right? As I mentioned, when we have a reaction, we think, well, this is the ideal amount. If everything goes perfectly, this is how much we think we're going to get. That is called the theoretical yield. Theoretical yield is if this reaction goes exactly as planned and there's nothing wasted, there's nothing lost, nothing, it goes, no problems, we anticipate that we're going to get exactly a certain amount by calculation, okay? In other words, I calculate, I think I'm going to get this amount. That's my theoretical yield. But when we actually do the reaction, the actual yield may be less. Actually, it's always going to be less, all right? It's less than we actually anticipated. So we want to find out what's the difference between these percentage-wise. What is the difference between our actual and our theoretical? And that is called the percentage yield. Percentage yield. And all you do is you take your actual, what you really got in the lab, divided by what you thought you were going to get, and multiply by 100. Okay? So let's say that theoretically we thought when 10 oxygen molecules and 5 carbon atoms, when they react in the lab, we thought we were going to get a perfect yield of 5 carbon dioxide molecules. But when we actually did it, we only got 4. Well, that means we got 4, we thought we were going to get 5, and that is an 80% yield. Okay, we only got 80% of what we thought we were going to get. Okay? So that's how that works. It's really simple. All you have to do is to just decipher which is the actual, which is the theoretical, and do the calculation. So here's a reaction, and it says when 36.8 grams react with excess chlorine, the actual yield is 38.8. Okay? 38.8 of this. And we want to know what the percentage yield is. So we actually got this amount. How much did we think we were going to get? Well, that's what we have to calculate. So what we have to do is we have to take this 36.8 grams here. All right, I'll walk you through the steps here. Our 36.8 grams, and we have to divide by the molar mass to find out how many moles that is. So 36.8 divided by its molar mass. The molar mass of C6H6 is 78.12. That gives us how many moles. That will give us the moles. Then we use the mole ratio up here in our reaction of this reactant to this product. It's a 1-to-1 ratio. So whatever the number of moles of C6H6 is, it's going to be exactly the same for C6H5Cl. So 1-to-1. Then we multiply by the molar mass of C6H5Cl to find out how many grams of that we have. So this is what we thought we were going to get, 53.0 grams. That's calculated. That's our theoretical. Did we actually get that? No. According to the problem, we didn't get that. We only got 38.8. Okay? 38.8. So we thought we were going to get 53, but we only got 38.8. Divide those, multiply it by 100. We got 73.2% of what we thought we were going to get. Okay? Now, if you prefer my table method, great. This basically is, okay, is your C6, H6. I'm just going to write down the two things that we're looking at. Okay? We are told 36.8 grams of this. 36.8 grams. That's your mass. So I have to, if I go this way, I divide by the molar mass. That's what I did right here. I divide by the molar mass of C6H6, and that gives me the number of moles. Then I use the mole ratio to go from one column to another column. Well, it's a 1-to-1 ratio. Okay? Again, I'm not looking at these two. I don't care about those two right now. The molar mass, the mole ratio is a 1-to-1, so I'm going to multiply by 1/1. That gives me the moles of this. Then to go to its mass, I am going to multiply by the molar mass, and that gives me the mass of my C6H5Cl, and that's what this is right here. That's the 53. But the problem says I thought I was going to get 53.0 grams. That's what I calculated, but actually I didn't. I only got 38.8, and that is a 73.2% of what I thought I was going to get. Okay, that's my percentage yield, the percentage that I actually got compared to what I thought I was going to get. Okay. Let's see here. Let's do this one. We might as well. Methanol can be produced through the reaction of CO and H2 in the presence of a catalyst. Okay, so we got this reaction. Looks like it's balanced. And it says if 75 grams of CO react to produce this, what is the percentage yield of, okay. So notice we're actually producing 68.4. That's what we're actually producing. So I know that is going to be my actual. I need to find the theoretical and then multiply it by 100. This is what we actually produced. So I'm going to take this amount right here, 75 grams CO plus H2, QH2. Okay, 75 grams. I'm given 75 grams of the CO. I need to divide by its molar mass. Well, carbon is 12, oxygen is 16, so that's 28. So I'm going to divide by 28. 75 divided by 28. That's going to give me 2.6, let's say 2.7, okay, 2.7 moles. Now I look at what's the ratio between the carbon dioxide that I have and what I want to produce. It's a 1-to-1. So if this is 2.7, this is 2.7 as well. Now I go down here and I'm going to multiply by its molar mass. Well, what's the molar mass of this? Carbon is 12. I've got 4 hydrogens, that's another 4, and an oxygen is another 16. So that's going to give me 16, 16, 32, right? 32, I multiply by 32, 2.7 divided by, or multiplied by 32, 85.7. 85.7 is what I thought I was going to get. I only got 68.4. So now this number goes in here, 85.7. Divide those, multiply by 100, and you've got your percent yield. Okay? All right, that is 9.3, all about limiting reactants and percentage yield. Okay, I will make another video that walks you through these Chapter 9 review questions. All right, keep working hard. Let me know if you've got questions. I am here to help as always.